Welcome to the course module of Communication System Engineering. And in this video, we are going to learn about the narrowband noise process. So let's begin this discussion. So first of all, in my previous lectures, I have already explained you about if we filter a white noise process, okay? If we have any white noise process, which is denoted by NIT, and whose power spectral density function is denoted by SNIF. So we have already seen in case of white noise process, the power spectral density will be a flat spectrum. Okay, so it will be a flat spectrum. So that we can see here in this particular picture. So this particular noise that we are considering is a white noise as well as a Gaussian noise process. So in my previous lectures, I have already explained you this Gaussian process means it is related to the probability density function. So the probability density function will be your Gaussian in nature, and power spectral density function will be white in nature. So this is why we are calling it as a white Gaussian process. Okay. So in my previous lectures, I have already given you the relationship. If we pass such a random process through a particular filter whose your frequency response is given by HF, then the output noise process, if it is denoted by N1T, then this power spectral density function of this output noise process N1T will be given by this particular expression. Okay. So if let us say the power spectral density of this output noise process is denoted by SN1F, then this will be related to the input power spectral density. Okay. So PSD SNIF, if it is known, then we have to just follow this relationship to find out what will be the output power spectral density function, right? So this way we have to actually calculate this output PSD, right? So here we can see this filters can be a low pass filter, it can be a high pass filter, okay, or it can be a band pass filter in this case, okay. So whatever be the filter, we have to follow this same formula, right? This particular relation we have to find out. So once we are able to calculate this output power spectral density out of this particular filters, then we will be able to calculate what will be the total power which is available output of the filter. Okay. So if this is N1T, which is the output noise process, okay, of this particular filter, then this total power PN1 will be calculated by following this particular expression. Okay, so we have to integrate this power spectral density function, which is the output power spectral density function. And this is we have to take, and then we have to integrate it over the pass band of the filter. Okay, so this minus W to W that I have written, it is actually belongs to the pass band of the low pass filter. So in such cases, we can see that in the case of low pass filter, this pass band, you can either make it minus B2 plus B, or you can also, by following the symmetric property of your integration, we can make it 0 to B, and here we have to multiply a factor of 2. Similarly, for this pass band of your band pass filter, we have to consider these 2 points, right? These two cutoff points, higher cutoff points and lower cutoff points. So these two cutoff points we have to know, and then we have to substitute here into this particular integration, and we have to find it out. Okay. So here we can see this is white noise process. It will have a flat spectrum, and normally when it is a double-sided spectrum, we are denoting it as a N0 by 2. So here you just make a small correction. This is not SXF. So because I have chosen this symbol to be SNIF for the input noise process. Okay, so it should be replaced with this SNIF, right? So now let's try to understand what is narrowband noise process. Okay, so as we can see that when we are passing such white noise process through a filter, okay, specifically white and Gaussian noise process through such filters, then normally what we have is it will remain Gaussian in nature. Okay, this output N1T will remain Gaussian in nature. The meaning is that its probability density function will have the Gaussian curve, but it will no more a white noise process. Okay, So we are saying it is no more white process, means it is not having this power spectral density function, which is flat spectrum, and it is extending from minus infinity to infinity. So because only such particular pass band it is only allowed to pass, and therefore all other where the we are having the stop bands at these particular portions, this noise process will become zero, okay, at the output of the filter. When it is multiplied and we will be following this particular equation, that time this output of this filters will only contain the noise content within their passband. Okay, outside the passband, because the filter itself is having its frequency response equals to zero, therefore the noise cannot pass it through, right? And therefore normally this output noise process cannot have the flat spectrum, okay, which is varying from minus infinity to infinity. It may be a flat spectrum, but the spectrum cannot extend from minus infinity to infinity, and therefore it will no longer a white noise process. Okay, so this is one of the very important point or fact that you have to remember. Now we have to see what is narrowband noise process. So normally, suppose if we have a white noise process and if we pass it through a narrowband bandpass filter, okay, let us say this is our filter. Then normally if you see, then the output of such filters, let us say this is the white noise process. If we pass it through a band pass filter, those characteristics is shown here. Okay, this is our frequency response of the filter, and it is mathematically, it will be denoted as HF equals to 1 within the pass band of the filter, and otherwise in the stop band this frequency response will become 0. Right? So it is having its central frequency at f equals to fc, right? So this is the band pass filter. So if you pass this particular noise process through such filters, then obviously if the output noise process is N1T, then this power spectral density function of S1F will be having this particular nature. Okay, so here you can see, because we have to follow this particular expression, okay, Sn of Sn1f will be equals to Snif multiplied with the mod of HF square. So obviously we are going to get a similar curve, okay, a similar PSD curve as we are having its frequency, means it is similar to your frequency response of the filter. The only difference here you can see that this magnitude has become now n naught by 2, okay, because we have to take HF whole square mod of HF whole square, and here HF is equals to 1. So this is the output power spectral density, okay, output power spectral density function, right? So normally when we are passing any white noise process through such a narrowband pass filters, then the output noise process N1T is referred as the narrowband noise process, okay? So sometimes it is called as narrowband noise process, or it is also called as narrowband bandpass noise process. Okay, so there are two ways of representing the narrowband noise process mathematically in time domain. So there are two methods or two way of representing it. Is the first one is in terms of in phase and quadrature phase components, and it may also be represented in terms of envelope and phase components. So here we will be using this particular result of in phase and quadrature phase component. So normally in phase and quadrature phase component, this narrowband bandpass noise process will be mathematically represented as this N1T will be represented as NCT multiplied with the cos 2 pi FCT minus NCT multiplied with the sine 2 pi FCT, where this NCT we are calling it as the in phase component, and this NST will be called as the quadrature phase component. So please note down that we are actually not deriving this particular expression right now. Okay, we will be deriving this expression in some other lectures, but at present we will be directly using this particular formula. Okay, so normally what happens in the calculation of the noise power in various communication systems, like in amplitude modulation receivers or DSBSC receivers or SSBSC receivers, we normally need to go for the calculation of the powers, and in that time we need to know what will be the power content of this in-phase component, what will be the power content of this quadrature phase component. So therefore, I will be just discussing how to calculate this NCT or NST, okay, that we have to look at. So suppose that if we wish to calculate this NCT, we have to follow this particular procedure. We have to pass this N1T, and we have to actually, this N1T has to be first multiplied with the cos 2 pi FCT. And then the resultant signal, if we pass it through a low pass filter of appropriate cutoff frequency, then we will be able to extract this NCT. Okay. So here we can see that because our N1T is given by this particular expression, I'm just multiplying it with the cos 2 pi FCT to get this NCT value. Okay. So if we multiply this with the cos 2 pi FCT, here you can see that this signal will be denoted as N2T. So N2T is, if you do this particular calculation, this calculation is very simple and straightforward. You please try to do this. Okay. So if we multiply with the cos 2 pi FCT, we are going to get this N2T equals to NCT multiplied with the cos 4 pi FCT plus 1 and divided by 2 minus NCT sine 4 pi FCT divided by 2. Right. So it is very simple to get. Please try to get this particular expression. Right. So once we will be able to get this N2T, and if you can see, if you pass this particular signal N2T through a low pass filter with appropriate pass band, then we can see that these two components, because here it is sine 4 pi FCT term, and here we are having the cos 4 pi FCT term. It means that this particular signal NCT is multiplied with the cos 4 pi FCT. So it is centered around somewhere in the 2FC, okay, at f equals to 2FC. Similarly, this NST component is again centered around your f equals to 2FC. And therefore, this 2 frequency component will be already rejected by the low pass filter, okay, because it is a higher frequency component. Now, here you can get another term which is NCT divided by 2. Okay, so the ultimate output of the low pass filter, if you see from this calculation, that this N2T ultimately that we are going to get after the low pass filter. Okay, so please write here one more expression. Okay, so that you have to write here that passing this N2T through the low pass filter, then the output of the low pass filter will be equals to NCT by 2. Okay, so this will be NCT by 2 is the output of the filter. Okay, low pass filter. So in a similar way, if you wish to calculate this NST, okay, quadrature phase component, this N1T has to be multiplied with the sine 2 pi FCT, and again it should be passed through a low pass filter. So similarly, we will be able to extract this NST component, right? This is a quadrature phase component of your narrowband noise process. So now we are generally interested what will be the power content of such noise process if we are passing such narrowband pass filter. First, we are obtaining the narrowband pass filter and multiplying with such multiplier, okay, and then passing it through a low pass filter. What will be the power content? So to understand the power content of this in-phase and quadrature phase component, we have to recall my previous lecture. Okay, so I have already discussed about the how to find out the power, what is the basic definition of the power spectral density. I have already discussed in my previous lectures. So recall that particular lectures, and those who have not watched that particular video, please go to that particular video first, and then you will be able to understand this lecture also. So just for recalling purpose, let us suppose that if we are having any signal, okay, which is denoted by GT, and if its Fourier transform is known to be GF, okay, then we can actually calculate the energy of this particular signal, right? So what we had did, if you remember that we actually had taken the GT to be a power signal, okay, it was having a very because it is a power signal, it was having its duration from minus infinity to infinity, okay, and therefore we have taken this to be a truncated version of the signal first, and then we calculated the truncated version signal's energy. Okay, so this was the energy of the truncated version of your GT that we have already seen in my previous lecture. So that can be calculated from minus infinity to infinity G square TD, G square capital T, small t dt, right? So this will be the formula for your energy. And then we had calculated what will be the power of this signal GT. So we have to simply put this limit t tends to infinity, and then we have to calculate this EGT upon T, right? So ultimately, I already shown that this power spectral density will be actually the definition of the power spectral density as GF is limit t tends to infinity, and we have to use the Parseval's theorem identity. And this EGT can also be calculated by calculating the mod of GTF whole square. Okay. So this was the actual definition of your power spectral density. Okay. So now one thing that we have to understand, suppose that if we are generating another signal, okay, if we are generating another signal MT, which is the scaled version of your GT. Okay, we are performing an amplitude scaling. So let us suppose that this MT is actually obtained after multiplying the GT by a factor of A, where A is the amplitude scaling factor. It can be greater than 1 or it can be less than 1. So if it is the case, then we can see that even if you calculate the Fourier transform, because it is a constant, the Fourier transform will be same as the previous case, but scaled by a factor of A. Okay, it will be multiplied by a factor of A. So this way we are going to get this particular signal. And if you wish to calculate what will be the power of this particular or energy of this particular signal MT, then it will be calculated EM equals to A square, then integration from minus infinity to infinity GT square T dt. Okay. Because this term will also come into the calculation A, and therefore we are going to get here this value as equals to A square. So if you calculate what will be the power spectral density of this particular signal MT, then that you can easily see that it will be actually SMF equals to A square SGF whole square. Okay, because this is equivalent to, if you substitute for it, you will be able to see that basically this SMF, if you calculate, if you following this particular expression, you will find that it should be A square limit t tends to infinity mod of GTF whole square dt. Okay, so if you see this calculation, what we are actually able to understand that this power spectral density function for a scaled version of any signal, that scaling factor should be multiplied with the original power spectral density function. Okay, so this scaling factor was A, so here we have to square it, and then we have to multiply this scaling factor with the previous power spectral density. So now you try to understand, if let us suppose we are having this particular signal NST, okay, NST by 2. So here we can see that because we are actually saying it is NCT by 2 or NST by 2. So if let us say that this N1T, okay, this N1T is having its power spectral density as N1F, in that case, if we multiply the cos 2 pi FCT to this N1T, then after multiplication of this, the power spectral density function of output of this particular function, okay, it will be equals to 1 by 4 Sn output F minus Fc plus Sn output F plus Fc. Actually, we are following the frequency spectrum shifting of the Fourier transform. Okay, so that we have to follow. So after following this, because we are multiplying it with the cos 2 pi FCT, it will have a similar impact onto the PSD also, as we have already seen in the case of Fourier transform. Okay, so normally in the Fourier transform, we have already seen that this is going to be a shifting of the original spectrum. In a similar fashion, the PSD is also going to be shifted, okay, a shifted version of your original PSD. But here we can notice that we are going to get this particular factor of 1 by 4. So why this factor of 1 by 4? Because here it is going to become a factor of 1 by 2. Here we can see that it is 1 by 2. So what we have did to obtain this NCT by 2, we are actually taking this N1T and we are multiplying it with the cos 2 pi FCT. And after that, we are actually passing it through the low pass filter. So because we have to follow this particular relation, it is a square SGF. And therefore, we can see that if we are multiplying the N1T multiplied with the cos 2 pi FCT, first it will be a shifted version of your original spectrum. One more modification you have to actually do. Okay, you remember here one small mistake here you can see. This should be denoted by SN1. Okay, it is not SN output, it is SN1. So remember that this is our spectrum. I have already shown here. It is SN1F. So it should be your SN1. Okay, and it should be a shifted version, and it should be shifted around your FC, right? So there F minus FC and SN1 F plus FC. And because of this factor 1/2, it will be becoming a square. So it will be a factor of 1 by 4. So this way, this N2T that we are going to get will have this particular power spectral density function, right? So ultimately, this will be the SN2F 1/F SN1 F minus FC plus SN1 F plus FC. So let me correct it here itself, otherwise you may get confused. Okay, so let me first make a little bit correction over here so that you should not be confused. So it should be N1. Okay, so let me make it as 1. It should also be N1. It should be N1. Then again, it should be N1. They're all N1. This is again N1. Then just make it. So similar way you can understand it is all N when it is not. There is a typographical error. Okay. So this should be N1, right? So just make it N1. So now you can see that after having all this, we can see this because we have to understand this calculation, right? So if we take this calculation now, you can understand this one. So this SN2F is nothing but the output of your after multiplying this N1T through the cos 2 pi FCT. So this is your N2F, right? This SN2F is the power spectral density function of this N2T. So once you will pass this particular signal N2T through the low pass filter, then because of the low pass filter, a certain component will be going to be rejected. Okay, some portion is going to be rejected and some portion will be retained. That we can see from this expression itself. All the higher frequency component will be get rejected. So that we have to see here. Okay, so here we can see this is our N1T, N2T, cos 2 pi FCT, right? So this N output T, this is the output of the low pass filter. Okay. So output of the low pass filter is actually denoted by N output T. So here we can see that if we following the same expression after passing through the low pass filter, the PSD of the N naught T, if you see, it will be having the same PSD, but now it will be restricted to this particular frequency band. Okay, so this frequency band is now restricted to this frequency band only. It means that it will be having a low pass filter. So because the low pass filter will be having a characteristics, like let us say it is having a characteristics which is varying from minus W to plus W. So within that particular band only, we are going to get the output. So that we can see it from the graphical procedure also. Okay, so if we see this power spectrum of in phase and quadrature phase component, so let us suppose we have already seen that our SN1F was this. Okay, if you recall, you can see this. Okay, this is the power spectral density function of our narrowband noise process. So if we take this power spectral density function, and if we perform this shifting of this particular PSD curve, okay, around the frequency component FC. Okay, so just to make a right shifting by a unit of FC, and again you can make it a left shifting by the same unit of FC, right? So this will be the shifted version of your SN1F, right? And this is again a advanced shifted version of your SN1, right? So this will be the values, and you can see because a factor of 1/4 is multiplied over here. So because SN1F was having its magnitude equals to N0/2, now this magnitude will become N0/8. Okay, because it is N0/2 multiplied with 1/4. So it will become N0/8. So this will be the shifted version of this particular spectrum. Okay, this particular power spectral density. Similarly, we can see that because it is centered at around FC, and if it is delayed by FC amount, this is going to be shifted around 2FC, right? So this is the spectrum around 2FC here we can see, and this is has to be shifted around this particular 0 axis, right? So it will be a shifted version. Similarly, if you make a left shift, you are going to get this particular spectrum, right? So this way you are going to get this two spectrum, and because we have to add these two spectrums together, so once you will be adding this two spectrum, because these two are the overlapping portion of your power spectral density function, and therefore the output we are going to get is N0/4. Okay, because N0/8 plus N0/8, it will become N0/4. So this is the power spectral density of this particular N2T. And here we can see that we are going to get this two extra components. One is at F equals to 2FC, and another at F equals to minus 2FC. So that we have already seen here. Okay, you can see this is the component cos 4 pi FCT, right? So because it is centered at 2FC, right? And therefore we are going to get this type of PSD curve, right? So once we are going to get this PSD curve, if you pass it through the low pass filter, after passing it through a low pass filter, obviously if we are having a low pass filter of bandwidth of W, in that case, this two frequency component will be rejected, okay? And only this portion is allowed to be passed, right? So the output of this low pass filter is denoted by N output T, and therefore this N output F will be equals to this particular power spectral density. So this will be the portion which will be allowed to pass, right? So this will be the actual output of your filter, and therefore we can calculate what will be the power of your narrowband noise process at the output of the low pass filter. So how to calculate that? We have to take this as an output FDF, okay, this output power spectral density function, and we have to integrate over the passband of your low pass filter. So that you can calculate minus W to W, you can substitute as N output FDF equals to N0/4, then multiplied with this 2W, okay? So that you can multiply, and this power of your output noise process will be equals to N0 multiplied with the W divided by 2. So you try to understand this particular discussion, okay? So I hope you must have understood how to calculate the power of narrowband noise process by seeing this particular calculations. Okay, so you do practice this particular calculation, because in my next lecture, I will be discussing about the how to calculate the signal to noise ratio for different communication receivers. Okay, basically we have to discuss about the EM receiver, okay, in which I will be discussing about DSPSC, SSBSC. I will be discussing about conventional AM. Okay, so how to calculate the signal to noise ratio. That time this calculation will be used. Okay, this calculation will be used. So I hope you must have understood this lecture. If you have any doubt regarding Anything, whatever I have discussed in this lecture, please let me know with your comments. Thank you for watching this video.